Good. I see the red light, so it's working.
Okay, awesome.
Okay, so just a quick question. So Alessandra, you asked me to add a little bit of math, which is not something that I usually do in talks, even to, with professional astronomers. It's just that we just talk. Couple of questions about your level. Are you all familiar with scientific notation?
Yes.
You can nod? Yes, good. How about calculus? Okay. No, good.
Less
No, I mean,
so.
I started studying calculus when I was in my last year of high school. So, perhaps you were much more advanced than me, which is totally fine. So in any case, I think I have only one slide, which is probably, with high level, but it just gives you an idea. You don't have to follow all the details. I don't have, I don't go from one step to the other of the equations, but it gives you an idea of the type of assumptions that we make and how we go from one point to the other. And then if if you're not familiar with the specific math, that's not a problem.
Okay, that's fine. I feel like some of us might know like the basic idea of calculus, but we are not all experts, that's for sure.
This is fine. I'm not an expert either. It's okay.
Okay, when should we start? How many minutes should we wait?
Should we start at 9:05? Is that okay with everyone?
Mm-hmm.
Okay, and Marta, do you have any slides that you'll be showing?
Yeah.
Okay, so let me enable you to do screen sharing. Hold on. Actually. Okay, I'm just gonna make you host.
Turn on the light because it will get dark very soon.
I made you the host, so you should be able to screen share now.
Okay. Yep. No. Let me just try, okay?
Okay.
Okay, so I have to quit and rejoin because Zoom has to update a little bit, so I will be back in a minute.
Okay.
Okay, would you make one of us host before you?
Yes, I'm
Okay.
assigning you.
Okay.
She can probably give us equations that are super complicated because then we can study them on subsequent weeks. I mean, not, super complicated, but like, right? Isn't that the point of having more time?
Mm-hmm. Yeah, I guess she could give them to us and then like not really explain them.
Yeah.
I was watching one of her things yesterday and she had some equations on her slides, but like she didn't really explain like she didn't like solve a problem with the equation. She was just like, oh yeah, this is kind of what you use to do it. Hello, Karina. Hey.
Welcome to the physics club.
Thank you.
I think we're going to start soon, and we can all just introduce ourselves when Marta gets on. Yeah. Hi again.
Hello. Can you reallow whole screen sharing, please?
Yeah, I just made you host again.
Oh, perfect. Now it works.
Wonderful.
No? Can you see my screen?
It's loading.
Let's see.
Ah, okay. Because I don't see my screen.
It just says Marta Volonteri has started.
Oh, there we go. Now we see it.
Oh,
Okay.
yeah.
Oof. This is harder than I thought. Okay, good.
And would you like us to put questions in the chat? Or...
Why don't you just interrupt me?
Okay.
I think, I mean, I didn't prepare this as a formal discussion, but more of a, I have a few points, you stop me when there is something that interests you, otherwise I continue. And then we just see how it goes.
Okay, sounds good.
Okay, so should we go up for a quick round of introductions?
Sure. Is everyone okay with that?
Just your name and why do you like physics?
Okay. Well, I guess I'll go first. My name is Alessandra, and I like physics because it explains why things happen around us.
All right. My name is Anushka, and I like physics because there is so much that we don't know, and it's fascinating.
My name is Lucian, and I honestly could not put a finger on why I like physics, but it's really cool to learn about the relationships between different things in the world.
My name is Karina. I like physics for the same reason that Anushka likes physics, and I just had a couple of really good teachers.
Okay.
My name is Ethan, and I just thought like the physics club would be cool because I'm taking like physics at Berkeley High, so I just thought it'd be cool to learn more.
Okay.
My name's Naomi. I don't know that much about physics yet, but I'm excited to learn about it.
Good. Well, my name is Marta, and I became a physicist a bit by chance, but I really enjoy it. And I think that the reason why I like physics is, is first I wanted to know why a chair is a chair. Why is a piece of wood different from a piece of glass? And then kind of by chance, I entered into astrophysics. And then by chance, I ended up working on black holes. And I just liked it so much that I stayed doing that for the rest of my life. Okay, so if you want, I can start. So as I said, I will share my screen, I will talk, but please do interrupt it at any time. I will see your faces. So, although I cannot see everyone at the same time, but just interrupt me and that will be fine. Okay. So black holes. So first of all, I'm an astrophysicist, meaning that when I talk about black holes, it's not about them as singularities or objects in general relativity or in modified gravity. But really black holes for me are something that I see in the universe, and I want to understand why they're there, how they arrive there, and how they interact with the rest of the universe. So if you think of black holes as, you know, related to wormholes or all the movies, that's not what I do. But what I do is still cool. So first, what do we know about black holes in the universe? We observe them. You know, you can think that black hole means something that is dark, because the definition itself of black hole is something that when something enters a black hole, even light, it just cannot escape anymore. So if light cannot escape, it cannot go from the black hole to us and tell us what it's doing. However, this is not the whole story, because black holes are very massive. And this means that whenever mass, a hydrogen atom, a piece of your favorite jam or whatever, gets close to the black hole, it starts moving very fast. It's just an effect of gravity. And if something moves very, very, very fast, close to the speed of light, mass turns into light. So we don't see the black holes from the inside, but we just see their surface, what is outside, because what is going towards the black hole is shining. There's another way of finding black holes, and I will get back to this. But in general, in the universe, we measure the properties of black holes. There are plenty at this point. There are, I don't know, billions of black holes that we know about. And they come in two groups, let's call it. One is called stellar mass black holes. We call them stellar mass black holes because they have a mass similar to the mass of a star. So M sun that you see here, well, I don't see my pointer, but you see here the term M with an underscore sun. This is the mass of our sun. If you're interested, it's 2 times 10 to the 33 grams. But the point is, stars, normal stars, everything that we see in the sky, have masses from about 0.8, the mass of the sun, up to several hundreds, the mass of the sun. And so if a black hole, if we see a black hole that has a mass in this mass range, you say, oh, this is called stellar mass black hole. Okay, these are not the black holes I work on. My black holes, my favorite black holes, are much more massive than that. Now, so here I put some images. You see here, the first one, why don't I see my, well, whatever. So here you see something with a galaxy called M87. And from the center, you see that there is a jet coming out. You see that bluish jet? This is telling us that there is a black hole in there. And in fact, on the right, you see the picture of this black hole. This was taken, last year? Yes, 2019, by the Event Horizon Telescope. This was on all the newspapers, so I think that you may have seen this picture before. So this is a close-up, just a very close-up of the same black hole that you see out there, except that the scale of these two images is completely different. They differ by about 8 orders of magnitude. So on the one hand, we see the tiny black hole in the center, but the jet that it launches from the very, very center of the black hole gets all the way out of the galaxy. This at the bottom is another black hole that I like a lot. It's called the Sagittarius A star. Yes, we give names to black holes. So Sagittarius A star is the black hole that is in the center of our own galaxy, the Milky Way. Since it's in our galaxy, we know a lot about it. And in particular, we know very well its mass, which is 4 million times the mass of the sun. Okay, 4 million times is very large compared to the mass of the sun or any star. You cannot make a black hole this much from a single star. So what I've been doing for the past 20 years or so is trying to understand how do we form these black holes and how do they get there. So we know these black holes from two ways. One is like in M87, when you see a jet or some very strong light that I will go back to. These are objects that we call quasars. And it's really a signpost. It's like, you know, a lighthouse telling us there is a black hole in there. This black hole is huge and it's doing a lot of stuff. Otherwise, there are black holes that are like ours, that is not shining, not doing anything. It's very, very boring, but also very nice because we can study it very well. The masses of the black holes that we have seen in this group, so things that cannot be made by a single star, are from about 10,000 solar masses up to 10 billion solar masses. Now, if 10 billion solar masses is not something that tells you much, it's more massive than all the stars in our galaxy together. So some of my black holes are more massive, have more mass in them than our entire galaxy. You have to take the whole Milky Way, compress it into one single point, and then you would get a black hole like this. So you can understand why I want to understand what's going on there, right? I hope. Now let me get here to one of the questions that Alessandra asked, which is, how do we form black holes? Or is there a minimum mass for forming black holes? I will give this example. So there are two ways of forming black holes. One is this that I will discuss now, that has mostly to do with these stellar mass black holes. And then I will discuss ways you can form these more massive ones. So for stellar mass black holes, for a normal black hole, what we know at this point very well is that they come from the end of stars. Not the sun is too small, but for more massive stars, once they die, they form a black hole. How does it work? So look at this picture here. I'm really bummed that I cannot see my mouse, but I hope that... Anyway, look at this picture here. It shows the physics that is at play. What is a star? A star is a sphere of gas. That's it. If you have a sphere of gas or any material, you have gravity. And gravity, by its own nature, will pull inwards. So it's this black kind of swishy arrows. So if you only have gravity, the star or whatever you have, the cloud, the gas that you have, will collapse. Now, in principle, if nothing happens and you continue the collapse, you will have exactly black hole. But in nature, things are not so easy. If you compress gas, in this case hydrogen, enough, you can create another force, which is shown here with the red arrows, with counterbalance gravity. So gravity goes in and you create a force which is exactly equal that pushes out. So the two forces balance it. What is balancing this pull of gravity? Nuclear fusion. Okay, we said that the sun or the star is a ball of hydrogen. When you have two nuclei of hydrogen that are very, very close to each other, they can merge, and in this merger, they produce energy. These are nuclear reactions, nuclear fusion. Every time you have this fusion between two hydrogen nuclei, a fraction of their mass becomes energy. It's about 0.7% of their mass. So you create energy by this fusion of nuclei, and this creates heat. Energy can come in many forms, and heat is one of those. And this heat expands the gas, so you create a pressure, and this pressure can exactly balance the force of gravity. And this is shown in this equation that I circled over here. These 4 equations are called the equation of hydrostatic equilibrium, and these determine the structure of a star. So a star, to be there, to be seen as a star, producing light, so not collapsing, not expanding, must obey all these 4 equations. In particular, I said that the middle one is telling you on the left-hand side, you have the energy produced by nuclear fusion. And on the right-hand side, so this is pushing in one direction. And on the right-hand side, you have the pull of gravity that is pushing in the other direction. And at each point, R is the position from the center of the star. So at each and every point in the star, these 2 forces have to balance exactly. And this is, this is just what happens naturally, because in the universe, in physics in general, things tend to happen in the simplest possible way. And so that's how it works. Now, this goes on for generally a few billions of years. The lifetime of a star depends on its mass, but I'm not going into details. Until just you run out of hydrogen. So as long as you produce nuclear energy in the core, you produce energy, so you have an equilibrium and you balance these 2 forces. The moment in which hydrogen nuclei stop merging, collapse occurs. Collapse means that gravity wins over anything else. So eventually the star runs out of hydrogen in the core. Nuclear fusion doesn't happen. So there is nothing to counterbalance this collapse. And poof, everything goes in. Actually, it's a bit more complex, because as you collapse the outer layers of the star, you actually have an explosion. And this explosion takes away part of the star. These are called supernovae. They're very bright events in the sky. And after this explosion, what is left of the star can just collapse. Collapse out to which point? Now here we enter in a realm that I haven't studied since I was at university, so I will refer you specifically to the Wikipedia. Chandrasekhar limit, it's very, very well done. So you can collapse stuff generally until you cannot push anymore. Or in some sense, you can collapse stuff, and here I mean stuff in general, but it's we will see it's electrons and protons, until you have filled all the space that you have. Now, when I say space here, is not just space in our normal way of thinking it, it's quantic space. In quantum physics, things, electrons, protons, all particles have energy levels. As you collapse and compress these electrons and protons, at some point they just have filled all the energy levels that they have. Now, if this is enough to counterbalance gravity, good. And what you have formed is called neutron star. The electrons and protons compenetrate each other, you form a neutron, and you just stay there forever. Neutrons all packed together. But if the mass of the star is too massive, above these Chandrasekhar limits, which is about 2.5 solar masses, then even if you have packed together all your protons and electrons, they form neutrons, nothing can stop gravity. And in that case, what we call it's collapse, and the object itself becomes a singularity or a black hole. Here I'm talking about things in general relativity. There are branches of physics that study modified gravity, meaning that GR is not the way, general relativity. Stop me when I say something like, acronyms that for me are just, so general relativity, there are people who say general relativity is not really true, or it's not all the truth. So let's go beyond. But for the moment, all experiments that we've done, every single one has proven generativity right. So what we expect is that if you cannot stop the collapse of a star, you will form a black hole. Or at least a black hole with a mass, which is a fraction of the mass of the star. So we believe that with this type of collapse, you can form black holes up to a mass of about 100 solar masses, 100 times the mass of the sun under normal conditions. But as I said, there are other ways to form black holes, and I will get back to it. So if we think, yes.
Is there a maximum limit on how large a black hole can become?
The physical size, not the mass. So in terms of physical size, the mass of a black hole, so the physical size of a black hole is directly linked, to its mass. It's called the Schwarzschild radius. So if you take a mass, so say a black hole has a mass of 1 solar mass, the Schwarzschild radius of that black hole will be 2 times g times the mass of the black hole divided by c squared, where c is the speed of light. So for each black hole that has a mass, there is only one radius, which is its size, and it's linear in mass. So the radius of a black hole is proportional to its mass. However, there are other radii that are associated to black holes. And I have a slide later on that shows some of these radii, but the size, it's the Schwarzschild radius. And it's very tiny. For a black hole like...
Oh, I was going to say, hypothetically, what would happen if a black hole sucked in all the mass in the universe?
Well, you would have to work extremely hard for that to happen. But let me go to this when I define the second radius connected to a black hole. Or if you want, I can look at it now. Let me see.
It's okay if you have an order then.
Okay, so let's go, it's here. So you see here, I defined what a black hole is, and we can go back to this. So you see here the equation for the Schwarzschild radius, 2gm, the mass of the black hole divided by c squared. Okay, so when something crosses the event horizon, this something becomes part of the black hole. But to be sucked into the black hole can suck in only mass within this other radius called the sphere of influence, which is again g. G is the constant of gravity, 6.667 times 10 to the minus 8 centimeter cubic grams divided by second squared. You don't have to know this by heart. It's just that, it's something that I write 10 times a day. But you see here that instead of having c squared at the denominator, I have something called sigma. Now, sigma is the velocity that stars have in a galaxy. The speed of light is 300,000 kilometers per second. The speed that stars, including our sun, have in a galaxy is about 200 kilometers per second. So you see the difference between these two radii is 300,000 divided by 200 squared. So it's about 10 to the 6. So the Schwarzschild radius, if you take the Schwarzschild radius to be 3 kilometers, which is the typical, this is the Schwarzschild radius for a black hole with a mass of like our sun, the sphere of influence, so all the material it can suck in, will be a million times larger. But stuff that is outside this radius cannot be sucked into the black hole. This radius. The term is the mass or the stuff or whatever that is energetically bound to the black hole. So you can always think of energy. If something has enough energy to fly away from the black hole, it will just not be sucked in. So everything that is outside this radius will not be sucked in. So for instance, for a massive black hole like in our galaxy, we are super safe. I mean, super safe. The radius that can suck in stuff in our Milky Way is about 10 times smaller than our distance from the galactic center, from the center of the galaxy. So we are about here where you see these reddish dots in this image of the Milky Way, and the center is at the very center. So there is just no way that our black hole can suck everything in. So black holes are not as powerful as you may think.
Can you explain how these radii have to do with Hawking radiation?
Nothing. So Hawking radiation is a quantum effect in the sense that, now this is, in quantum physics, a particle, say an electron or a proton or a full hydrogen atom or a person, but a person is just too big. You cannot determine its position and velocity with a given accuracy at any time. So the product of velocity times position of a particle is all, I mean, the accuracy with which you know the product of position times velocity for a particle is less than a number, which is called h, which is a constant. Now, Hawking radiation has to do with this uncertainty principle in the sense that if you don't know if your photon or your electron, you cannot really say if it is inside or if it is inside or outside this Schwarzschild radius, just because of this uncertainty principle. So there is a possibility or a probability that you lose some of the mass. So this is called evaporation because it's a probabilistic effect. Now, the only black holes that can evaporate within the lifetime of the universe are super tiny, are smaller than the size of the Earth. So for astrophysical black holes, like those that I study, Hawking radiation is just nothing that we care about.
Thank you. Can you also tell us about the Bondi radius?
Oh, awesome. I removed it from this slide. I thought it was too... Oh, how do you know about the Bondi radius?
I did some research.
Ah, okay. So here I define you the radius of influence of the black hole as the radius within which mass is bound to fall eventually into the black hole. This is not totally true. This is true for stars. For the Bondi radius, it's exactly the same. So it's again g, the constant of gravity, multiplied by the mass of the black hole. But at the denominator, instead of having the velocity of stars, you have the velocity of gas, which is called the sound speed. Well, it's called sound speed. Well, anyway, the sound speed has a value for normal galaxy between 10 and about 1,000 kilometers per second. So the Bondi radius is about the same size as the sphere of influence. So again, if the Schwarzschild radius is 3 kilometers, the sphere of influence, the influence radius and the Bondi radius will be about 3 million kilometers, which is nothing. Again, I mean, for a galaxy, it's nothing. But so both the Bondi radius and the radius of influence have the same meaning, which is determining how far away from the black hole the universe can feel its attraction.
Thank you for answering my questions.
Good. Okay, so let me go back here. So to the massive black holes, more about their properties. So as I said, if you look at this galaxy here, M87, and this jet that is launched. Now, if you think about this object, is very bright. So you see all this fuzzy orange light, that's the whole galaxy that hosts the black hole. It's actually one of the most galaxies that we know in the most massive galaxies that we know in the universe. And this black hole is one of the most massive that we know in the universe. The black hole in M87 has a mass of 2 billion solar masses. When it emits light, because something is going towards it, it becomes very bright. And these are black holes that we call quasars, from quasi-stellar objects. They were discovered in 1963. This is a picture of the first quasar ever discovered by Martin Schmidt, actually in California. So these objects are very luminous, meaning that their luminosity is comparable to the luminosity of an entire galaxy. So like in this case, 10 to the 11, 10 to the 13 times the luminosity of the sun. This means so in a galaxy like the Milky Way, you have about 100 billion stars. So the luminosity of the Milky Way will be about 100 billion times the luminosity of the sun. And now you have these objects called quasars that have similar luminosities. But then you can prove, and the proof is written here at the bottom, that the size of these objects is very small. It's comparable to the size of the solar system. How do we know that? This was actually, one of those pieces of astrophysics that to me is always amazing. So you stare at this quasar, 3C273, this is its name, but there are many others that we can look at. And we see that the light that comes from these objects changes over time. And while if you look at the galaxy, a normal galaxy without a quasar, so not a quasar, the luminosity is constant. You look for 10 to the 7 years, so for 1 million years, the luminosity doesn't change. While these objects, the luminosity can double in about a week. So these first told Martin Schmidt and all the people working there that these cannot be galaxies because they have very different behavior. But also, if something changes in luminosity by a factor of 2 in 1 week, this tells you that this object is very tiny. The reason is that information, so light, so if you see that the light changes within a week, it means that something from one side to the other of the object has changed and has communicated information to us within a week. So the size of these objects is 1 light week, is 1 week traveling at the speed of light. So you take the size, will be the velocity at which you move, c, multiplied by the time. So if the time is 1 week, you just have a size of 1 light week. And this is about the size of the solar system. While the size of a galaxy is about 7 orders of magnitude larger. So this is telling us that these objects cannot be galaxies. They must be something that is very, very, very small. Powerful, but small. So this was just, this was a revolution in astrophysics, by the way. It was really fascinating to learn the story about this, because these objects should not exist. In 1963, there was nothing that made people think that such objects could exist. There was just nothing in the physics that we know could explain it. Until Lyndon Bell and some other people came up with an explanation. And they said, okay, let's try and see what they are. Are they stars? Well, let's calculate this. No, the luminosity, so as I said, the luminosity is what we measure, the light that comes from it, can be expressed for any physical process that we know as an efficiency that I call this epsilon with the Greek letter, multiplied by the mass of the object, multiplied by the speed of light squared, and then divided by time. Luminosity is just power, so it's energy per unit time. MC squared is energy, you know, the famous Einstein's E is equal MC squared. So this is a variation on this, in the sense that it's true that energy is MC squared, but normally not all the mass goes into energy, but a fraction of this, and this fraction is epsilon. And then since in astrophysics, we cannot measure energy, but luminosity, so the energy per unit time, we just divide it by time. That's what we have to do, right? Now, you can infer, not measure, but infer the lifetime of a quasar. Just because you see so many quasars in the universe, you know that they cannot be on for a very short time. So just from the number that you see in the universe, knowing the age of the universe, you can say that the lifetime is about 10 to the 7 years. The argument is like this. So if I see, suppose that I see 1,000 galaxies, and about 100 of these are quasars. This means that the fraction of quasars is 10% of the galaxies. You can also say that all galaxies become quasars for 10% of their lifetime. So you can make a connection between the number that you see and the fraction of time that you can see them. Since, I mean, the way we are here now, we can observe for 10 years, but not for 13 billion years, which is the age of the universe. So we have to use these indirect arguments. Anyway, suppose now that the lifetime is about 10 million years. Now let's go back to this equation. So here you have, what you want to find is the mass. C is the speed of light, you know its value. Time is 10 to the 7 years. Let's assume that these are stars. As I said at the beginning, the power of stars comes from nuclear fusion. So when two protons merge and produce nuclear energy, a fraction 0.7% of their mass becomes energy. And then, you know, does all the stuff that I told you, creates thermal pressure, fights against gravity, and eventually leaves the stars and comes to us. Now, if you use this epsilon, this 0.007 in this equation to derive the mass, you will see that the mass that you get is larger than 10 to the 7 solar masses. So this cannot be a star. Why? Because a star with a mass of 10 to the 7 solar masses collapses immediately into a black hole. The gravity, as I said at the beginning, you have a balance between gravity and some pressure inside that pushes backwards. Now, if you have a mass of 10 to the 7 solar masses, you can push backward just for a very, very short time, just in a few seconds. Everything I said about star evolution, poof, it goes into black hole. So the point is, the only explanation that you can use with stars will lead to the formation of a black hole in a second. But if this has been alive for 10 million years, then this has been a black hole for 10 million years. And so that's the solution. We have black holes. Also, you can prove, and this is related again to energy is equal to mc squared, that for black holes, this efficiency epsilon is not 0.007, but about 10%. In reality, it's between 0.06 and 40%, but on average, it's 10%. So if you go back to the equation of the luminosity, and now you try to derive the mass with this new epsilon, you find that the mass is between 10 to the 6 and 10 to the 8 solar masses. So from 1 million to 100 million solar masses. So finding these quasars led to the conclusion that in the universe, there are these black holes with masses above 1 million solar masses. There is just nothing you can do about it. They are there, and they produce a lot of light. So we have used quasars since 1963 to learn about black holes. And what have we learned? Again, let's go back to here. So let me put this in the context of a galaxy. So here you see the Milky Way. The picture in the middle is a picture of the Milky Way, taken by Alex Mellinger. I should, the reference, sorry, it's covered by this black circle, which is actually a sphere. You should think of this in 3D. This black sphere is called a dark matter halo. So in a galaxy, this is actually not to scale. So the galaxy is actually much, much smaller than the dark matter halo. So the mass of a galaxy, so everything that we see, all the stars that we see in a galaxy represent only about 10% of the mass of this dark matter halo. Now, I'm not going to talk about dark matter. It's also another fascinating topic, and I'm sure you could be curious about it, but dark matter is what makes most of our universe. Don't ask me what it is because we don't know. That's it. But we know it's there just from measurements, just because we can weigh a galaxy and we know that the mass of the galaxy is 100 times larger than if we sum the mass of all the stars that we see inside. So you have a dark matter halo, then you have the galaxy itself, so all the stars, and then you see here in the middle these kind of blackish clouds. This is gas, hydrogen with some carbon. And then at the very center, you have the massive black hole. In our case, as I said, it's called Sagittarius A star. It has a mass of 4 million solar masses. And here you can really see the scale. The black hole is invisible on this picture. It's just too tiny. The size of the dark matter halo, no, sorry, let's start with the size of the galaxy itself is about 10,000 light years. The size of the dark matter halo is 100 times that, but the size of the black hole is 1,000,000 times less. The size of these regions called sphere of influence or Bondi radius instead are not super tiny, are just tiny in the sense that they're about 10 to the 4 times smaller than the size of the galaxy. So these are all the scales that we have just for one galaxy. But then we have to do this or understand this for all the black holes and all the galaxies in the universe. And this is actually what I do. So what I do is not to look at it. Oh, here, that was a problem. See, it was not as bad. So what I do is really to look at many black holes, many galaxies, and try to understand the whole population. How do we get this stuff here? So I showed you a Sagittarius, I show you 3C273, I showed you Sagittarius A star, I showed you M87. So 3 black holes that have names. Now there are many more that do not have names. So in this figure here, I collected number of black holes in galaxies. So here, what you see at the bottom, oops, in this figure, you see the mass of the black hole, this is the y-axis, as a function of the mass of the galaxy, this is the x-axis. And you see here that there is basically a diagonal distribution. In small galaxies, you have small black holes. In large galaxies, you have large black holes. This is what we observe, right? So what we have to find is an explanation for why this is so. But as a rule of thumb, if you have a galaxy and multiply its mass by 10 to the minus 3, you get pretty much the mass of the black hole. So there is really this tight connection. So this led us to think that galaxies and black holes evolved together in the universe. Now the universe is about 13.7 billion years. And we know that galaxies have an age of about 10 billion years or so. So black holes must also be as old as that. So what I do in my normal day is to try to explain the picture that we have today. So this figure that I showed you and the galaxies that we see today, like here at the top right, you see how nice, oops, sorry, I pressed something. Okay, the galaxy here on the top right is a galaxy like those that we see today. It's a nice, cute galaxy with lots of stars and, you know, a nice shape. But what I try to do is to reverse time, or to see what happens in the early universe when galaxies were more like the one here at the bottom, all very massy. You know, it takes time for galaxies to grow, and at the very beginning they have a more active life. It's like for humans, really. When galaxies are young, they do a lot of things. They can run, play, you know, go around. And then as they age, they become more and more tired. They cannot do things so much, and they become like this. It's called the quenching of galaxies, the quiescence of galaxy, and it's just something we observe. So what I try to connect is the early universe, where things were happening all the time, to today, not only in terms of galaxies, but also in terms of black holes. So I'm really trying to evolve a galaxy and the black hole at the same time to see what happens to them. Okay, so before I move on to gravitational waves, and do you have any questions on this?
Yes. I have 2 questions. One, how does the dark matter halo impact your measurements of black holes? Like, are there any things you need to do to like make sure that it doesn't like interfere, or do you just not?
No, it does. Actually, it does impact the way we measure the mass of the black hole. I don't have a slide here showing the math, but I can probably find it. Let me just. Let me see if I can find. Okay, can you see? Let me stop sharing and then share again. But now I will share this one. Okay, in this figure, I'm showing pretty much how we learn about the mass of black holes. What we measure is how the velocity of stars changes as we move away from where we think the black hole is. Now, so here, sorry, there are a few integrals, but don't worry about it. The main point to show here is that depending on how mass is distributed, if you have a black hole, it's just a point source, meaning that, you know, as I said, the black hole is a very, very, very tiny size. So all the mass is concentrated in one point. if you measure the velocity as you move away from an object, scales with the mass within the radius divided by the radius. This is just by equating, again, it's always about equilibrium. So this is the centripetal force. So when you move in a circle, the simple fact that you're moving, so with the velocity v, gives you velocity. Sorry, gives you a force, because you have a velocity. So velocity means an acceleration, and acceleration means a force. At the same time, if you're moving around an object, there's also gravity. So if this m is, say, me, the small case m, and the large case m is the sun, I can calculate the velocity of me around the sun using this equation. So the velocity of me around the sun does not depend on my mass, because here you see these two the little case m goes away, and depends only on the mass that is inside where I move. Now, suppose that I have only the sun or only a black hole. I have a mass in one specific point, but nothing outside. So m here will be just a number. So the velocity squared will go as 1 over r. So it decreases as I move away from the black hole or from the star. If you have studied the solar system, that you will see that this is the case. But if I have dark matter or stars or anything around the black hole, the mass is not concentrated all in the center. It's not concentrated in one point, which is the black hole, but is spread around. So if I calculate the velocity in this case, the velocity will not decrease with radius, but it will be increasing. Okay, so if I only have a black hole, the velocity of stars as they move away from the black hole will be lower and lower. If I do not have a black hole, but only have stars and gas and dark matter, the velocity as I move away from the position where I think the black hole is will increase. So now if I have a black hole, what I will see is that close to the black hole, I will have a velocity that decreases, and then we start increasing again. Now, this point where the two curves intersect tells me the mass of the black hole. Now, if I have stars and gas, I can just count them, right? And so I can calculate this curve. But if I have dark matter, I cannot see it. So dark matter is actually a source of uncertainty in the measurement. You have to make some assumptions. The case where this was studied best, again, is for the same black hole that we already talked about twice, which is called M87, and can make a difference of about 2 in the mass of the black hole. And so I've seen that if I don't go full screen, I can actually see my mouse. So if you don't mind, I will actually continue to go without going full screen. Okay. Other questions?
So there doesn't have to be a black hole at the center of a galaxy. It can just be a swirl of stars and dust.
Yes. In fact, if there is a black hole or not is determined by how you form a black hole. And in fact, it's really, well, let's say in 2008, I proposed that finding galaxies without a black hole is going to tell us how black holes were formed. And so now there are people who work on observations. As I said, I'm a theorist, so I don't observe with telescopes. But there are people who are observing the universe, trying to find the signature of these missing black holes. It's not that they're already missing. It's just that the physical conditions that are required to form a black hole didn't happen there.
What is
I've
it?
no, sorry, go ahead. I was just going to ask, and is it possible for a black hole to not be spinning, or do they have to be spinning?
That's a very long answer. So I had a slide on that with some nice equations, but I removed it because I thought it was not interesting. But anyway, so what we think is that at birth, black holes have spin. The reason is, if we go back, let me go back, navigator. If we go back here, okay, go back to this picture. The moment you stop having force from the inside and gravity pushes in, the star or no, the proto-black hole will collapse. Collapse requires conservation of angular momentum. I wish I had a pencil and paper, but so angular momentum that we usually call with uppercase L is equal to mass times velocity times radius. Now, if initially you have a given mass and all this mass is within a large radius, you will have a large angular momentum. Now you take this same mass and now you compress it into a small region. So your radius will be decreasing. This means that the velocity must be increasing because angular momentum cannot change. The total angular momentum is a conserved quantity that cannot change. So if I decrease the radius, I must increase the velocity. Increasing the velocity means that I increase my spin. So that's why we think that black holes at birth have spin, just because it's a consequence of their collapse. But what happens later, it depends. So it's very, very hard for me as a physicist to think that there are black holes with exactly zero spin, because it doesn't need much to change something from zero to a non-zero quantity. But we think that most of the black holes, stellar mass black holes, have a relatively low spin. While for massive black holes, there are two competing theories. One that says that most of them have high spin, so spin fast. This is my theory. And then there is another group of people, mostly in England, who thinks that black holes should have a low spin. Now, we are theorists, so we propose these theories, and in principle, observations should tell us which of the two is right or wrong. But observations are giving conflicting results. Some observations say spin is zero. Some observations say spin is close to 1. So we don't really have an answer.
What would the effects of determining whether it's one or the other be?
It has to, well, the most immediate ones. So let me go back here. Okay, so you see this efficiency that I wrote here for black holes to produce energy, produce light. Here I said epsilon is about 0.1. In reality, oh, I can write. These efficiencies between 0.06 and 0.4, where 0.06 is for a black hole with zero spin, and 0.4 is for a black hole with spin of 1, actually 42. So the way black holes produce energy is directly related to how fast they spin. And if you think of this not just for one black hole, but for all black holes in the universe, the amount of energy that is being produced is very different. Or turning the argument around, the amount of mass that was eaten by black holes to produce the same amount of energy changes by about an order of magnitude in the two cases. So this is the first point, which really has to do with the relationship between mass and light. The second has to do with gravitational waves, which is something that I wanted to talk about later. And in particular, the way we measure gravitational waves is affected by the spin of black holes. If black holes have spin exactly 0, it's much harder to detect gravitational waves because they're in some sense simpler. If black holes are spinning, you have additional features in the gravitational waves that allow us to see them more easily. So this would be the consequence. So these are the reasons why we care about learning about spins. Other questions?
I actually, when I was doing some research, I saw that the black hole in the middle of our galaxy is a quiescent black hole, and I was wondering exactly what that means.
Good, I have a slide for that. So when we say, so quiescent black hole contrasts with quasars. So quasar is exactly the opposite of a quiescent black hole. So a quasar is a black hole that is producing a lot of light. And as we see here, this means that if it is producing a lot of light, there is a lot of mass that is converted into energy. A quiescent black hole, like our own, instead is not producing light. So this is a picture, shows the center of the Milky Way. Over here at the center, there you have the black hole. Now contrast this, so look at this quasar. You see this blinding light? It's a lot of power. It's very bright. Now, if you look at the center of the Milky Way, you see basically nothing. All these little dots are not black holes, are stars. So our own black hole cannot be distinguished from a star. In fact, you can measure its luminosity. You see here the close-up in X-rays. X-rays are just tracing gas that is very, very hot, and gas near a black hole is always very hot. So this X-rays is the best picture that we have of the black hole in our own galaxy. And if you measure the luminosity, is basically pretty much the same as the luminosity of our sun. So for a quasar, you have a black hole that is as luminous by itself as the whole Milky Way. For Sagittarius star, for our black hole, it's as luminous as a single galaxy. Although their masses are, I mean, the masses of the two black holes are not very different. So it really has to do with how much mass crosses from outside into the event horizon. A quasar has a lot of mass going in. A quiescent black hole is starving. I mean, there is no mass that can go inside.
I saw something on another slide about, I think it was hyperbulge, something bulge and like classic. What is that referring to? It was a graph.
Bulge.
It was the one with the graphs massive, yeah.
Okay,
Pseudo
so here,
bulge, not hyper.
Oh God, okay, in the figure, right. Okay, what is a bulge? Let me go back here. I will show you. Now that I have back my mouse and I can show you, I'm very happy. You see my mouse, right? Yes, good. Okay, so this is the Milky Way. This, you see here in the center, this big ball or yellow ball. This is the bulge. So a galaxy is made of the central region, which is called the bulge, which is a sphere pretty much made of stars, many, many stars. In our bulge is, I think, about 1 billion solar masses. And then you have some other stars that are scattered around the galaxy. So if I go to this other galaxy here, the bulge is this central region. Again, you see that it's very bright. And then you have the gas and stars that form a disk here. So we call the central region the spherical bulge, and the outer disk, the disk. Now, the reason why here you have this distinction, so elliptical galaxies are galaxies that are made only of a bulge. They have no disk at all. Galaxies with classic bulges are galaxies like this, where you have the bulge and the disk. Pseudo bulges, oh, this is just, people who have too much time to spend finding names, because a pseudo bulge is a bulge that is not very, very dense. So it's kind of a half bulge. Honestly, I mean, it's a subtlety. But the point is that, so here, what I show here on the x-axis is the total mass of the galaxy. If I took only the mass of the bulge, this relation would become tighter, meaning that the points would move towards, you see here, these gray diagonal lines. Because the mass, if I take only the mass of the bulge instead of the total mass of the galaxy, what happens is that these points here move to the left. And so everything tends to sit in this region. So this is a not answered question in astrophysics. We have some theories why black holes know better about the bulges of galaxies than all the galaxy, but we're not totally sure. Bulges form when two galaxies merge, because you see here the disk is a rotating thingy. The bulge is not rotating. If you smash together two disks, what happens is that the rotation cancels out. So all the stuff that is rotating in the disk ends up going into the bulge. So if this is the way bulges form, probably something happens during mergers also to black holes. And we think that this has to do with accretion, so the black holes grow more during mergers. But again, there's been a lot of controversy. This has been going on. These relationships have been discovered between 1995 and 2000. So at this point, it's 20, 25 years. And still, we haven't been able to fully explain them. We kind of have polite guesses, we have theories, but the observations are just not clear enough to, usually what you do if you're a theorist, you make a theory, and then observations have to say, well, your theory matches our data, so we don't throw it away, or your theory doesn't match your data, so we throw it away. So at the moment, no theories could really be thrown away, so there is possibilities.
I have a question. How strong would evidence have to be for a theory to become more than just a theory, or for it to be proven, in quotation marks?
Well, technically, you cannot ever really prove a theory. You can only disprove a theory. And usually, so you can say that a theory is in agreement with your data up to a certain statistical level, but you can never say that it is true, because that would mean 100%. And in physics, there is no 0 and there is no 100%. it's always, we always have a statistical approach. We can say, this is good up to 99.999999, but we never get to 100, basically by definition. So usually, to say that a theory is in agreement with data, we use a definition in statistics, which is called 3 sigma, which means that you have the probability that this measurement, this comparison between theory and data is wrong, is less than 1%. It's actually less, it's 99.9, so it's less than 0.01%. Again, there have been cases where, despite this very high probability, things have not worked out. Sometimes because there are errors in the measurement. It's normal to make mistakes. We all do it. And so sometimes you think that you have measured something correctly, and it turns out that, your telescope was not working, your computer had a bug, you put a 2 in the equation when there was no 2. So these things happen. But the important thing for us scientists is that, well, if we're wrong, we just accept that we're wrong and we move on. Sometimes I had theories that didn't match the data, and so I'm sorry, I liked my theory, but it's wrong, so I accept it. But some were actually in agreement with data, so I'm still happy.
So would you say that nothing in physics is 100% certain?
No. It's actually the basics of science. You need to be able to measure something, and to be able to measure something, you need to know that your measurement cannot be perfectly accurate. You need to know that no matter how good your experiment is, it cannot be perfect. I told you at the very beginning, the limit, we have an absolute limit, which is the quantum effect. I told you that you cannot measure the velocity and the position of a particle with a precision that is higher than this famous H value. So we just have to be aware of that. If you want to be a physicist, you have to be aware that there is no perfection. There is always a small degree of uncertainty, which is actually good because it pushes you to do as well as you can, 1, and 2, not to just accept things, because you always have to see how good something is. So to me, it's very important to know that in physics, you cannot just accept something to be correct. It can always be questioned. Then we have assumptions, which is a bit different. For instance, in early 1900, when cosmology, when the evolution of the universe was first studied, there were assumptions. We will assume that the universe is homogeneous and isotropic. Homogeneous means that the density is the same everywhere, and isotropic means that the distribution of galaxies in the universe is the same in all directions. Now, let me show you a picture, if I have it, of... Yes. Okay, look at this picture. This is actually a simulation, but this is a distribution of galaxies in the universe. Would you say that this is homogeneous, so the density is the same everywhere? No. So, we had this assumption, and obviously it was not right. In reality, it is correct, because once you take very, very large scales, the mean density, it's true, is the same everywhere. But it was one of those cases in which you make some assumptions just because without those assumptions, you cannot do the math. It's, the way it is. But then you know that you have made these assumptions, so you know that there may be something wrong. And so at each step, you have to go back and say, is my assumption correct? Or is my assumption going against it? And so for many, many years, up until very recently in the 90s, this was a big deal. Is the universe homogeneous or not? Only with very, very large data sets, you can actually prove that this assumption on large scales, the scales that count on these specific equations, is correct. But if you try to use the same equations in our nearby universe, it fails completely. Again, it's correct within some limits and it's wrong in other limits. You just have to know which are these limits.
Thank you.
Okay. Let's see, it's about 7:20, and I think I will have to go at about 8 because I need to prepare dinner. So let me pick and choose some topics. Okay, so we can talk a little bit about okay, let me give you a choice. How about that? You choose. So we can talk about black hole formation. So we talked about black hole formation in galaxies, but we can talk about the formation of massive black holes. Sorry. The formation of black holes from the collapse of stars, but we can talk about the formation of the other massive black holes. Or we can talk about gravitational waves. Or we can talk about simulations of the universe and black holes in it, because that's what I do. What do you prefer? Let's see raised hands. Black hole formation. Gravitational waves. 1, 2, 2.5, 4. Okay.
I can't raise my hand, but I want that one too.
Okay, so we go with gravitational waves, which is what I was going to talk in next. Gravitational waves is basically something that, well, it's been very popular in the last 5 years because it was the big discovery for us in the field. And also I'm spending a significant time of my time working on a gravitational wave instrument. I mean, I don't make the instrument, but on the theory behind it. And so I'm happy that you like them. Okay, massive black holes and gravitational waves. So first, if you want to see a picture of gravitational wave, you can see it at the bottom. This green thingy is the space-time. Now, normally, space-time is flat, at least in our universe. But when a gravitational wave passes through space-time, it modifies its shape. So this green area, which should be flat, you see that is now all kind of shrinking. So this is what happens when a gravitational wave passes through. And what we want to do is to detect them, not only for the black holes that we have seen now, but also for all black holes in the universe. Now, for the moment, we have seen gravitational waves using this instrument. Actually, this is LIGO. This is a piece of LIGO. There are 2 LIGOs in the US, and then there is Virgo in Europe. These are all interferometers. So you have a central point here, and you have 2 very large, what we call arms, which are these 2 bits. And these are built so that you can measure the passing of a gravitational wave. So if you measure the length of these arms at all times, and you use a laser for that, you know what it is, like, 3 kilometers, 3 kilometers, 3 kilometers. Now, if a gravitational wave passes through, as I told you, changes the shape of space-time. So at one point, one arm will become a little longer, and then it will go back to its size. And then when the wave passes through the other one, it will be the same. It changes size for a little bit and then goes back. So you can find that the gravitational wave passed through that bit of space by measuring the change in the size of these two arms. This is what we have done on Earth. These LIGO, Virgo, and are all on Earth. And the size is a few kilometers. This is something that cannot see in my black holes. Why? The explanation is shown here. Now, gravitational waves are characterized by frequency in the same way that light is. You know that light has a frequency from high frequency, which is, for instance, ultraviolet or X-rays, to low frequency, going to optical, infrared, and radio. So you have the full electromagnetic spectrum. Gravitational waves are exactly the same, because like light is just electromagnetic wave. Gravitational waves are gravitational waves. So they share pretty much, well, no, they share most properties of light when we think about it as a wave. But it's, so if you have a frequency, the way you can associate the frequency of a gravitational wave to a black hole is by thinking that gravitational waves are created generally, or the strongest gravitational wave events, those that I care the most, are produced when two black holes merge. What does it take for two black holes to merge? They have to cross each other's event horizon, so each other's Schwarzschild radius. So now Rs here is the Schwarzschild radius. So this is the frequency at which an object moves when it's moving at the speed of light on a circumference of radius, the Schwarzschild radius. Okay. So one moment, one black hole is circling the other black hole at the Schwarzschild radius. The next moment, when it gets closer in, gone. Well, it takes a while to merge. They do a lot of stuff. It's called merger, ring down, and so on and so forth. But the whole point is that the frequency of gravitational waves is directly related to the Schwarzschild radius of a black hole. But since the Schwarzschild radius of a black hole is written here, 2gm divided by c squared, then if in this equation you put 2gm divided by c squared here, you will see that the c is a constant, 300,000 kilometers per second, g is a constant, so the only thing that remains is the mass of the black hole at the denominator. So the frequency of gravitational waves for merging black holes is about 10 to the 4 hertz, which is, something that we have on Earth easily. But then it depends inversely on the mass of the black hole. So the larger your black hole, the lower your frequency. Or the smaller your black hole, the higher your frequency. So for LIGO Virgo, so the frequency that you can determine just depends on your instrument. And specifically, the frequency is the inverse, or has to be comparable to the inverse of the size of these arms. So if you have a high frequency, you can have small arms. If your frequency is lower, then you have to go to large arms. So for LIGO Virgo, which is on Earth, so it has to be much, much smaller than the size of the Earth, you are limited to a small size of these arms. So you can only probe high frequencies. High frequencies meaning, again, about 10 to the 3 hertz. If you take 10 to the 3 hertz here, the mass of the black hole that you get is about 10 times the mass of the sun. And this dot here means mass of the sun. So this is great, but it doesn't see my black holes, because I told you my black holes are about 1 million solar masses. To get 1 million solar masses here, you see that the frequency becomes about 10 to the minus 2 hertz. So you have a much lower frequency. If you have a lower frequency, you need a larger instrument. So the instrument that I'm working or involved in building is called LISA. It's basically the same principle that you have here. You see this triangle, but you have it in space. So it's one triangle that moves, this is the sun, that moves in the solar system. The size is about 2.5 million kilometers. So it's much, 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 much larger than the Earth. But being so large, you can prove the frequencies that correspond to the merger of black holes with masses from 10,000 to about 10 million solar masses. But that's not the end of this. I told you there are black holes with masses of 10 billion solar masses. These are emitting a frequency that are of order of nanohertz, 10 to the minus 6 to 10 to the minus 9 hertz. The size of the instrument that you need to detect these waves is about the size of the entire galaxy. And we have that instrument. We haven't built it. We're using the galaxy. So in the galaxy, there are objects called pulsars that emit pulses of light with very, very good frequency. So you can time the frequency, the time of arrival of these pulses from the pulsars. They arrive always at the same time. No, every second, actually every millisecond, puff, 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 for many, many years. But if a gravitational wave passes between us and the pulsar, then the whole space-time changes. So we will not see the pulse from the pulsar arriving when it should, because you have changed the distance between us and the pulsars. So by looking at all the pulsars that we can in the galaxy and seeing if there are glitches, if at some point we don't see the pulse when it should come, we can reconstruct whether a gravitational wave passed through. And the super most exciting thing was that this week, it was, they posted a paper showing that we have detected gravitational waves from this. It's still a small evidence. So we were saying earlier on about the, at which point you say that something is a discovery. Usually you say that, you know, if my confidence that I've measured something is 99.99%. In this case, the measurement is not that good. Is at about 70–80%. So there is still room for, perhaps it's just noise. Perhaps we haven't seen a gravitational wave from super, super duper massive black holes yet. But it's getting close. So, I mean, this measurement with pulsars have been going on for tens of years. Actually, the measurement improves as you have many, many years. So this week for us was just phenomenal. Now we have black holes from low mass black holes, gravitational waves from low mass black holes, gravitational waves from super duper massive black holes. So we know that the physics is the same on the two scales, which is something that we always assume, but again, it's physics, so you need to prove it. And eventually, hopefully, we will get gravitational waves also from this instrument, which is planned for launch. It's a satellite, which is a joint NASA and ESA. So NASA is the US, ESA is Europe effort, mostly ESA actually, and it's set to launch in 2032. So right around the time when, you know, if you decide to become physicist, you can actually be professional physicist. I would be close to retirement, but you know, for me it would be still exciting. So this is the current picture. So in some sense you can think really, so it's the way you can think of gravitational waves is the same as thinking as telescopes on Earth. You can have different telescopes that see different frequencies, and so they see different objects in the sky. And with different detectors for gravitational waves, we can see different types of black holes all over the universe. Well, not all over the universe, but for a large fraction of the universe.
How do the gravity waves affect time?
They don't affect time per se. They affect space-time. So when I showed you this green thingy here, it seems it's in 3D, but it's actually in 4 because you have space and time together. It's just that our eyes cannot, you know, we are unable to draw it. But you can think of this either as changing the shape or the size of the detector, or changing the time at which, or changing a little bit the time. So making the detector longer would be the analog of saying that time is slower.
When you detect a gravitational wave, what does that tell you about the black hole?
It tells you two main quantities. One is the mass of the two black holes plus the mass of the newly formed black hole. And then it tells you the spin, so a fast, it tells you the spin of the newly formed black hole. It's a bit harder to measure the spin of the two black holes before the merger. And then it tells you how far away this happened, so the distance between us and the black hole. So then with this information, we can use the information, the masses and the spin to test the models that we have. For instance, black holes can, you know, I showed you the case of black holes forming by the collapse of stars, but then you can have black holes merging one with the other and the other and the other, so in a sequence of mergers. And the spin of the black holes will differ whether they had 0 mergers before the one that we detect, or they had several mergers. So you can use the spin to know how this black hole was born, by itself or with many other black holes and it merged together. Same with the mass. Stellar physics tells you that you can form a black hole if a stellar mass is up to 50 solar masses, and then there is a gap, there is a region in which there is no black hole formation, the whole star explodes, and then there is a second region where you can form black holes again, and then there is a second gap again where the star explodes, and then you can form black holes again. So if you find a black hole with a mass which is in these gaps where there should be no black holes, then you have to find an explanation for why they are there. An explanation, for instance, is that you merge two black holes that were not in the gap, and then you form a black hole that is more massive. This is really top science right now, because LIGO Virgo, when was it? 2 weeks ago, announced that on May 21st, 2019, they detected the merger of the most massive low mass black hole ever, which has a total mass of about 150 solar masses, when after the merger, but one of the progenitors has a mass of 80 solar masses, and this black hole should not be formed according to stellar evolution. So there must have been something else that formed this black hole. So for instance, it merged with another black hole before, or there are other solutions, primordial black holes that have to do not with stars, but with inflation, or some weird stuff that we don't know yet. So measuring these parameters, we can either infer information about our models, or again, rule them out, or in any case, learn about the physics that generated this thing that we observe. Other questions on this? Okay, so what do I actually do? What I do is to make universes on my computer. In these universes, I put galaxies and black holes, and then I check if my universes look anything like real universes. Then, being a theorist, is that theories make predictions, and then experiments have to check them. So what I do is to predict what Lisa, so this satellite, may be seeing. So this is an example. This is from some calculations a few years ago. So in this figure, you see the x-axis is the mass of black holes. The y-axis is the age of the universe. Today we're here. And as we go back, we go closer and closer to the Big Bang. So if you go here, this is a black hole that has a mass of 1,000 solar masses. Sorry for the logarithm. If you just, no, this is 1,000. That existed when the universe was about 200 million years. Now, 200 million years is super young for the universe, huh? It's the time when the first galaxies formed. And then this, as I said, galaxies and black holes grow with time. So this yellow black hole, as time goes on, becomes more and more massive. So you see, we start here from about 1,000 solar masses, and we end here with 100 million solar masses, 10 to the 8 solar masses. How do you grow in mass that way? What do you put into the black hole to make it more massive? You can put two things, either another black hole, so a merger of black holes, and this is what each circle represents, or you can throw gas. So instead of throwing a full black hole, you just throw some hydrogen, well, hydrogen, little bit of helium if you want, but mostly hydrogen. And so when the black hole grows by eating gas, it's when you see here, for instance, you see it better in this case, when you have a smooth growth in mass, but without a circle. Okay, so my models actually predict or model all these processes, how black holes grow in mass, how they merge with the other black holes. And then I compare all the dots basically here with what we can see with gravitational waves. And I compare this smooth evolution, this gas accretion, with what we can see with quasars. I told you quasar, the difference between a quiescent black hole and a quasar is that the quiescent black hole is not eating any gas. A quasar is eating a lot of gas. So a quasar is something that is moving in this plot. Can I see quasars in the whole universe? Well, I can see quasars in this region here, the gray shaded area. This means that I can see quasars as far back in the past, as far away from us as about half a billion years after the Big Bang. So more than 12 billion years ago. And I can see black holes that have masses of about 1 million to 1 billion solar masses. Now, if I go to my favorite satellite, LISA, it can see everything that is in this light part here. You see from this, anything inside this curve with 10, all the way to this other symmetric curve. So with LISA, you can probe, you can really measure the properties of black holes in this region here that we cannot see with our telescopes. We cannot see with quasars. So that's why for me it's important, because my models, part of the work that I do, cannot be tested, cannot experimentally tested with our telescopes. We need something else. And this something else is gravitational waves. And so that's my interest. So the questions that I've been working on in the last years are the following. How many galaxies host black holes? Which means when, where, and how black holes form. How black holes grow in mass over time. So I have to count both how much gas goes in and how many mergers with other black holes they have. And then how do black holes actually merge? So how long does it take for black holes to merge when they get in the same bit of the universe? So I hope that this works. Not really. Let me try again. Okay. So this is a simulation of a bit of the universe. This is actually a formation of a galaxy a bit smaller than the Milky Way. Each of these dots here, the white dots, are black holes. Everything else that you see, well, black is empty space. All this blue is dark matter. The green is gas. And these purplish thingies are stars. So when I said that I make a universe on my computer, this is exactly what I do. I create the whole history of a galaxy with all its components. You see here these black holes forming galaxies, and then they swirl around and they move as the galaxies move. You saw here just the merger of galaxies. You see the formation of stars. And you see how when stars form, they kind of create a spherical shape. This is the bulge we were talking about. And we also form this disk of gas in stars. So we are really witnessing here the formation, the growth of galaxies. And at the same time, when you have gas, stars, and dark matter, you also have these white dots, which are the black holes. The black holes are doing what I call their dance. It's a dynamical effect. They're moving under the effect of gravity, and they're going closer to the center, and then they're kicked out, and they go closer in. And at some point during all this dance, they also merge with other black holes, and they accrete gas. So you cannot see it here because, there is no post-processing, but in some of these phases, the black holes are shining as quasars, and in some of these phases, they're merging, so we can see them with gravitational waves. And you see everything that happens in the universe. For a galaxy, life is complex because you have all these streams of gas that go in from different bits of the universe, you merge with other galaxies. Galaxy mergers are at the same time the most fascinating and most destructive parts, because when you smash two galaxies together, let me see if I can go back. Fortunately, I got a new laptop. No. But when you smash two galaxies together, I think I have something else here, right? So let me show you. This is what happens when you smash two galaxies together. It's a bit of a mess. You saw here how you started from two disks with the galaxies and that end up with just a ball with some stuff around. These are the formation of the bulges that I was discussing. And so when you want to study black holes in the universe, you have to take into account all this stuff. So you have to start from cosmology, because you need to know how many galaxies are around, how often they merge, what happens when they merge. Do I more often merge big galaxies or small galaxies? And then every time two galaxies merge, I have to look at what happens with the gas in them. Does it turn into stars? Does it turn into black holes? Does it go into the black hole and grow? And then I have to go on, and then I have to follow the little, remember, galaxies are big, black holes are tiny. So I have to zoom in the very center of the galaxies and try to follow. This is the evolution of two black holes. You see two black holes, 1 and 2, that originally were in two different galaxies. And now they're moving and getting closer and closer until they form a binary. For a black hole to form a binary means that these two black holes cannot be detached anymore unless you give them a lot of energy. So in general, they will just stay there, and at this point, there are a couple of black holes, they're binary, but they're not emitting gravitational waves. They're just too far away to emit gravitational waves. Remember that the emission of gravitational waves is very important, is very strong when they are separated by their Schwarzschild radius. At this point here, the two black holes are separated by 1,000,000 times the Schwarzschild radius. So they have to travel a long, long time, both in time and space, in order to emit gravitational waves. So basically this slide summarized my work. I put together everything from cosmology to gravity to processes of called dynamical friction. I had a slide on that, but I don't think we will go into it. And gas storms is how black holes interact with gas. Stellar scattering is how black holes interact with stars. So you have to put really everything together, then shake it well, and see if what you obtain is a universe that makes sense or not. If the universe that I create matches all the properties of the universe that we know, for instance, how many galaxies are there, how many quasars are there, then I can use this universe, mock universe, to predict things that we cannot measure yet. For instance, how many gravitational waves Lisa will see. And then in 12 years, Lisa will tell me whether all this modeling was correct or wrong. If it's correct, I will be happy. If it's wrong, well, I had fun working on it, so I'm still good with it. But so this is, in the last 5 minutes, the summary of what I've been doing in the last too many years. And I will keep on doing for as much, because it's really a lot of fun for me. So do you have some more questions on my everyday life as a scientist, I mean?
Do you ever use like quantum computers to do your simulations?
No, quantum computers are, no, quantum compute. So I use supercomputers, but not quantum computers. So quantum computers for the moment are more of an experiment, and you cannot use them to actually make calculations. So what we use are supercomputers that are huge. On average, when we run a simulation, it runs on the equivalent of 1,000 of a normal computers at any given time. And even running on these supercomputers, they're national computers. So there is, in the US, there are some centers. I don't remember now, but I think that at Livermore, there is one center for supercomputer, which is just close to where you are. Lower is Livermore Labs. so even using those computers to run one, to create one of these universes takes about 2 years of real life. So there is a lot of, so these are, I mean, in general, when you get to this type of experiments, they're, well, expensive, but also time consuming, which means that if you make a mistake, well, it takes 2 years to redo the experiment. Sometimes you do make mistakes. We found that there was one of the assumptions in one of our simulations that was not ideal. I mean, we started running the simulation in 2015, and then in 2017, when we were close to the end, we discovered a new effect. But at that point, we couldn't go back and rerun everything. So we just have to be aware that there is this new effect that we have not taken into account.
So it takes a really long time, huh?
Yeah. That's why I'm old.
If quantum computers are developed, do you think it would help speed up the process of simulating something?
I'm not an expert on computer engineering, so I don't know what their performances would be. In general, the problem with these simulations is that technically we say they do not scale well. So usually what you, in a simple way, you can think that if you double the number of processors in your computer, then the time it takes to run the same simulation will be half. The fact that these simulations are so, have so many different scales, meaning from cosmology to small scales, means that this is not true. If you double the number of processors of computers that you use to run your simulation, your speed increases only by 30%. So we're often limited by the physics that we're putting in and not necessarily by the computational means.
Does anyone have any last questions before we wrap up?
I have just one more question, and it's got to do with the shape of black holes. I know oftentimes, like, if you look up a black hole, then it'll show a picture of like this really, really deep funnel, I guess, with the singularity at the bottom. But how would that look in 3 dimensions? Like, what happens to the space around it?
Okay, so usually a black hole is basically a sphere. So it's a hole, but it's a sphere. Meaning that it's the hole in 3D will have the same radius in all directions. So when I think of black holes, I think of spheres, and that makes my life very easy. In fact, even if they are spherical, however, you have generativistic effects that cause the light that you see from them to have weird shapes. So for instance, this is, so in principle, this is a 2D version. So you have to imagine this in 3D, but in 2D, this is the circumference of a black hole. And you see that it's not perfectly spherical, and it's not that the black hole is not spherical. I mean, we cannot say whether it is not or it is or not. But since you have generativistic effects, bending of light, this is redshift, you will see asymmetries in any case. But to me, the easy way to think of black hole is a sphere that is a hole.
So then the galaxy that's around the black hole, would the galaxy also be spherical, or is it flat like the images show?
Well, unfortunately, this is a computer screen. So if I look, let me see if I have, okay, do I have a nice galaxy? Well, galaxies are in 3D, so the bulge, so let me move this away. So the bulge is a sphere. The disk is actually flat. So do I have an, oh, look, oh, good, I have this. Okay, so these are galaxies where you see only the disk, not, so there is a little bulge here, but you see these are disks. So disks are flat. So this is seen face on, this is seen edge on, but instead the bulge is just a sphere of stars.
What causes the galaxy to be flat? Why isn't it round?
It's the rotation. So you remember I said this before, there is conservation of angular momentum. Angular momentum means mass multiplied by velocity multiplied by radius. So if material is that is falling onto the galaxy's angular momentum, it has to rotate at a given distance from the center. So since this material typically comes, and angular momentum is a vector, so it's meaning that it has a direction and not only a magnitude. So since it is a vector, it has to conserve the same direction throughout. Having a direction means that you form a plane of things. But anyway, so if material were not rotating, you would not form something flat. It has to do with the amount of rotation that mass has when it reaches the galaxy.
Is that also the reason why our solar system is flat?
Probably. No, I'm not an expert on planet formation, but it's a very similar picture. So there were some things, molecules, atoms that had some angular momentum, so some rotation as it approached the solar system. And so yes, it creates the same picture. And in fact, there are some instruments. One is a radio instrument called ALMA that has detected protoplanetary disks, so systems where you have the star and you have a disk pretty much like this one, made, which is continuous of stuff, but where you see some gaps, which is where planets are forming. So we think that the process is very similar, so it's related to rotation and the way energy is transferred.
Thank you.
Thank you so much for your time, Marta.
Oh, thank you.
I'm sorry we kept you for 2 hours.
Oh, no, I had blocked out 2 hours. I hope that you're not too bored at this point.
Oh, this is awesome. Thank you so much.
Yes, this is a great opportunity.
I'm glad that you liked it. There was not enough math, I'm sorry, but I usually think in terms of intuition more than math. But if you need more math, just let me know and we'll send you something.
Wonderful. Thank you so much.
Thank you, everyone, for being patient and listening to me for 2 hours. And I hope that you have a wonderful weekend.